Alright, so double integrals over general regions. So for single integrals, the region over which we integrate is always an interval, but for double integrals, we want to be able to integrate a function f not just over rectangles, but also over regions d of more general shape. This definition makes sense because because R is a rectangle, and so our double integral of our function f has been previously defined. The procedure that we have used is reasonable because the values of f of xy are 0 when xy lies outside D, and so they contribute nothing to the integral. This means that it doesn't matter what rectangle R we use as long as it contains D. A plane region D is said to be of a type 1 if it lies between the graphs of two continuous functions of x. That is, D is equal to at xy, where x is in between a and b, and y is in between two functions of x, where g1 and g2 are continuous on a, b. Some examples of type 1 regions are given below. So basically what we were doing with our iterated integrals is we were taking the area. So again, we're always going to have, the surface above. So here's the surface above whatever area, and our area is always going to be on the xy plane. All right, we could, we are going to do ones with, we're going to do triple integrals, but right now we're just showing you the area underneath whatever surface that we have. And so what we did last class is, instead of, I'll just try to draw this again. So here is, again, x, y, and z. What we did is we had some region above, all right, but that region, let me try to do that better. But that region was just, some type of rectangle. And so there wasn't really much shape to our actual there wasn't much shape of our actual region D. It just looked like a rectangle, and so therefore we had numbers. All right, but now that we're going to have some curvature to our actual region, those are going to be defined by functions. That's what's going to give us our shape. And so therefore, instead of going from double integral a to b and c to d, where those were just some values given a region, now what we're able to do is have an area underneath a surface that looks like, it has some form or shape to it other than a rectangle. And so how we're going to define this is that, this is going to be the top, bottom approach of type 1, is where kind of very similar to finding the area when we were looking at calculus 1, where we go left to right and then top to bottom. That's how we kind of wrote our function out. In this case, we're going to go from left to right first. So a to b. Again, we want to do that because those are going to be actual integers. And then we're going to go from, again, g2 of x, the top function of x, to the bottom function of x. All right, so the top bottom approach, f of x, y. And again, since these are defined by y, that's going to be dy dx. And that's how we're doing all of these. It depends on our shape how we want to do it, all right? And the thing is, it doesn't matter which direction we go. We could use a type 1 approach where we do top bottom, or we could do a type 2 approach where we do left to right. And if we do left to right, here our c's and d's are going to be our integers, and so therefore y is going to be the outside integral, and on the inside integral is going to be our functions that are defined by x. So one way to make sure that you always do this is that when you write your double integrals, say, oh hey, y equals c, y equals d, and then you have two functions, y equals all right, not y, but x equals, because these are going to be our x ones, x equals h of 1y, whatever function it is, and x equals h of 2 h sub 2y. And then of our function, fxy, and then dx, dy. Again, this is just using Fubini's theorem. Again, it says that it doesn't matter which direction we go, whatever looks easiest for you when we're actually looking at our region. So I'm going to do example 1 and 2, and then call it, and then do the next two, then do the next two. So the first thing that you're going to want to do is you're going to want to draw the region of whatever shape we have, and we got to look at what we're bounded by. And so we always want to draw the D. That's going to be our region. So therefore, we go from y. So we have our region y equals x cubed, and x is greater than or equal to 0. So what that means is let's go ahead and just draw this region. So let me change up the colors. So here's our region. And one good thing, if you're uncertain of where they actually intersect, over on the side, say, oh, if y equals x and y equals x cubed, we can say x equals x cubed because they both equal y. Bring their x over, we get 0 is equal to x cubed minus x. Pull out an x, we get x squared minus 1. And so we're getting all these values. We get x equals 0, x equals plus or minus 1, but because x has to be greater than 0, we just use the positive 1. So we know they intersect at 0, 1. So I'm just going to go from 0 to 1. And then also, for the y's, we also know where they intersect. When I plug in 0 for x, I'm getting 0, and when I plug in y, I'm getting 1. Again, plugging in 0 to that function, plugging in 1 to that function. Alright, I'm really plugging into both functions, alright? So, we go from 0 to 1, and now let's go ahead and graph what they look like. Y equals x is just, whoa, I don't know why I put a 1 there. Alright, y equals x is just a, I'm going to go ahead and put the straight lines. Y equals x, or the dots, is defined by that. And then, let's change up the colors. I don't want y'all to get confused. So y equals x is given by that function. And then I'll give this another thing. And then x, let's see, what is it? X cubed. So if you remember, x cubed, is doing this thing. And then it continues to go up. And so I'm going to go ahead and just highlight our region right there. All right, and I'm just going to go ahead and do the left to right. So our x values are going to go from 0 to 1. So from left to right, we have 0, 1. And then we do top bottom. Looks like y equals x is on top. And on the bottom, we have y equals x cubed. So let me make sure I write x equals 0. X equals 0, x equals 1, and then the integral. Now, you don't have to write x equals 0, x equals 1. You can just write 0, 1. And then we have, I just like doing it because it helps me remember. Let me write this function down here, y equals x cubed. So y equals x cubed, y equals x. And then we plug into our function, x squared plus 2y. And then again, dA can be written as dx dy or dy dx. And we're going to be able to find the volume underneath this region. So again, y is going to be the inside, so dy, and then x is going to be the outside. Again, that's why I write, x equals and y equals. And so again, I'm going to take the integral first of 0, 1. So I'm going to take x cubed and x. I'm going to go ahead and do the x squared plus 2. I'm going to integrate that with respect to y. And so I'm going to get x squared y plus y squared. And that's going to be from x cubed to x. And now on the outside I have just the dx. So now I'm going to go ahead and plug in my x values. So 0, 1. I'm going to plug in x. I'm going to get x cubed plus x squared. And then minus, then I'm going to plug in my x cubes. and I'm going to get x to the 5th, and then x cubed squared, so x plus 6, plus x to the 6. And that's it. I can rewrite that without, the parentheses, so I'll just do that. 0 to 1, I'll just read x cubed plus x squared minus x to the 5th minus x to the 6th. Again, you don't have to write, with it in descending order in terms of exponents. Just go ahead and keep it that way. And then let's go ahead and integrate it again. So now we're integrating with respect to x, so we'll have 1/4 x to the 4th plus 1/3 x cubed minus 1/6 x to the 6th minus 1/7 x to the 7th, and we're going to go from 0 to 1. We're going to plug in those ones, and we're just going to get 1/4 plus 1/3 minus 1/6 minus 1/7, and then let's go ahead and do that. We're going to get 23 over 84, just getting a common denominator and doing all that. And so we get 23 over 84, and that's it. All right, so hopefully you're finding this is not, it's so small. We gotta make it bigger. All right, hopefully you're finding that this is not going to be too complicated. All right, so example 2, express D as a region of type 1 and also a region of type 2, and then we're going to evaluate the double integral in both ways. And so I'm going to go ahead and I'm going to draw my region again. This is the first thing I want to do. So I'll just try to remember what I did. So I graphed it, this way. And it says it's enclosed by the region x squared and y equals 3x. So again, I'm just going to set the two equal to each other. And then I'm going to bring the 3x over, and I'm going to get 0. Pull out the x, I get x minus 3. And so that means that I have, for my x-axis values, from 0 to 3. And then those are all by 3, so 3, 6, 9. Because when I plug in, these values, I'm going to get 0. And when I do that, I'm going to get 0, 0. So here's going to be an intersection. And then I'm going to plug in 3, and I get 9. And 9's the other intersection. All right, so y equals 3x is just a line. And y equals x squared is a parabola. And that's a beautiful line. So here we have our region inside the two. And now I made it too big. And now we're going to be in between the two. All right, so let's go ahead and do that. All right. So we can do, let's go do a type 1 first, and then we'll do a type 2. So we're going to do our x. Our x is on the outside first, and then we're going to do our y's on the outside. So when I look at this, I can think of, left to right. So I'm going to say x equals 0, x equals 3, and then what's on top, what's on the bottom. I'm going to say that's y equals x, and this is y equals x squared. Whoa, that's not x over here. That's 3x. So that's 3x. All right, so then what I'm doing is I'm going from top bottom now. So top's y equals 3x. Bottom is y equals x squared. And then we have the function x, y is the surface. And again, we're doing y's on the inside, x's on the out. All right, so now I'm going to go ahead and integrate. 0 to 3. All right, integrating this with respect to y. It looks like I'm going to get, whoa, what did that happen? All right, xy squared, 1/2 xy squared, 3x, x squared, dx on the outside, let's go ahead and do that. So let's just keep working. 0 to 3, we're going to plug in our 3x. We get 9x cubed, so 9 over 2x cubed. Over 2x cubed. That's not a cube, that's a square. All right, minus, plug in the x squared. We're going to get x to the 4th, x to the 5th, x to the 5th over 2. And again, you could pull a one half out if you wanted to and just get 9x cubed minus x to the 5th dx. Let's integrate that with respect to x now. And so we're going to have the integral. So 9 half x cubed be 9 half x to the 4th divided by 4, so 9 over 8 x to the 4th. Minus, and then x to the 5th over 2. We're going to get x to the 6 over 6, so x to the 6th time over 12. And we're going from 0 to 3. So now we're going to substitute in. Looks like we're going to have a big old number. I'll just go ahead and say, I'll do it this way. 9 over 8 times 81 minus, put the 3 in there, so 729 over 12. 729 over 12 minus, and then plug in 0. That's nice. All right. And so, let me get that negative out. And so I have 9/8 over 81 minus 9/8 times 81 minus 7/29 over 12. It's going to reduce to 243 over 8. All right, now we're done. Well, we're not done, because now we're going to show you the other method as well, and we're going to go the other way. So let's do it where we're going to do the integral where we have y is equal to 0 and y is equal to 9. And another way to write y equals 3x, if we're writing it in terms of x, it's x equals y over 3. And this is just going to be x equals the square root of y. Again, plus or minus y, but because we're in the quadrant that we are, we're going to take the positive. So now we're going to do the top-bottom approach. So it looks like on top is 3x and on the bottom is a square root of y. I'm sorry, so now we're doing right-left. And to far right is going to be square root of y, and then the left is going to be y over 3. So x equals square root of y, x equals y over 3. And then, of course, x, y, dy, dx, dx, dy. And so we're going from 0 to 9. And now we're going to take the integral with respect to x. So it's going to be x squared over 2. So 1/2 x squared y. And now we're going to go ahead and we're going to plug in square root of y over 3. And we have dx, dy, so just dx, I'm sorry. Whoa, that dx should not be there. And so now we have, oh, I'm sorry, it should be there. That should be dx, that should be dy, because y is the outside function, and that's x. All right, so dy. Now we're going to go ahead and plug in, so 0, 9. We're going to plug in radical y. We're going to get 1/2 y squared minus, now plug in y over 3. We're going to get y cubed over 9, so 1/18 y to the 3rd dy. All right, integrate it once more. And now we're doing with respect to y, so y to the 3rd, so 1/6 y cubed minus, and then y to the 4th. 4 times 18 is 72 y to the 4th over 72, and we're going to plug in our values 0 to 9. Let me make sure that you see that's a 4. And so we get 1/6 times 729 minus, the good thing I have a 0 for the second one, 9 to the 4th. A fun thing to do. 6,561 over 72. We subtract, and what we get is 243 over 8. Alright, so I'm going to stop there and then continue with the next videos.